Welcome everyone. Today, we aren't here to talk about how to write a better CI script or how to fix a Jenkins bug. We're going to explore a paradigm shift in the entire software delivery architecture. We'll dive deep under the hood to see how we can evolve from fragile, high-risk manual delivery to an AI-driven autonomous architecture, truly achieving stable delivery for long-running applications. Look at these numbers. We spent the last decade building automation, but the result is that the average team now maintains over a dozen different tool chains. Cognitive load is crushing senior engineers. Automation has hit its ceiling. Meanwhile, the teams that first pivoted to AI-native delivery have increased their deployment speed by 75% and drastically cut costs. Why? Because they no longer write static scripts. Instead, they've introduced intelligent agents capable of autonomous decision-making. Why do we need to change? Because we face two irreconcilable conflicts. On the left is the eternal struggle between dev and ops, one wants speed, the other wants stability. On the right is the cognitive load crisis brought on by cloud-native tech. Think about it. How long does it take for a new hire to independently release a feature today? We may have automated the pipelines, but we haven't automated the decision-making process. All the pressure is still on human shoulders. So, how did all of this evolve? Let's first clarify the core concepts and see how we leaped from the era of hard-coded scripts to the age of AI-driven autonomy. Here is a straightforward comparison. DevOps 1.0 is essentially static automation. It executes exactly what you script, and if it encounters an unknown error, it simply crashes. DevOps 2.0 or AI-native delivery introduces agentic workflows. Agents don't just execute tasks, they diagnose errors based on context, propose fixes, and even self-heal in controlled environments. In other words, the system shifts from working by instruction to working by objective. This is a typical AI-native architecture diagram. Pay attention to the MCP router in the middle, the Model Context Protocol. In the past, we had to write plugins for every single tool. Now, after a developer commits code, MCP standardizes context delivery. Security, testing, and code agents work in parallel to autonomously analyze the impact of the change. A multi-agent collaboration network forms inside the system. That is the foundation of autonomy. Now that we've covered the concepts, let's see how these things are actually implemented in the real software development lifecycle, or SDLC. From code commit to production deployment, every single step is changing. SCM is the single source of truth. But in the past, it was just a cold storage vault. Now, through the MCP protocol, LLMs can directly read and understand your entire code base. You're no longer using grep to search for keywords, you just ask the system, where is the authentication logic implemented? More importantly, MCP ensures that the AI gets the latest, most accurate context, drastically reducing the chances of it making things up. Let me show you a concrete example. On the left is the grep we are used to. Searching for auth returns hundreds of results that require manual checking. Hit next, look at the right. Under the AI native architecture, you input natural language, and the system uses vector retrieval and AST analysis to directly pinpoint the specific file and line of code. It even mentions in passing that you're missing a fallback logic for refreshing the token. This is a direct reduction in cognitive load. Senior devs, think about this question. When facing a massive test suite, throwing hardware at it and adding runners is our most instinctive reaction. But that treats the symptom, not the cause, and it's extremely expensive. The truly elegant solution is B. If you didn't guess right, that's fine, because test intelligence is exactly the core technology we're going to break down on the next slide. This is the classic test pyramid. The base is a massive volume of unit tests. Platforms like Harness have introduced test intelligence TI technology. The core principle is that AI analyzes the AST abstract syntax tree of the current commit and cross-references it with the historical test coverage graph. It can precisely calculate exactly which tests are affected by the specific lines of code you changed. Instead of running 5,000 tests that take half an hour, you now only run the relevant 15%, finishing in 2 minutes with zero compromise on safety. Moving past CI, we arrive at CD. Many teams blur the lines between continuous delivery and continuous deployment. The key difference is whether that final step requires manual approval. In modern CD architectures, GitOps is the gold standard. We no longer manually type kubectl commands on servers. Instead, we write the desired state into Git. Reconciliation agents in the cluster continuously pull that Git state. If someone violates protocol and manually tweaks a live configuration, causing environment drift, the agent will instantly override it back to the standard state defined in Git. Running fast isn't enough. You also need to run stable and secure. Next, let's look at how security and stability are being redefined under the AI-native architecture. The core concept of DevSecOps is shift left. The later a vulnerability is found, the more the remediation cost grows exponentially. Today, we don't just demand code security, we demand supply chain security. Have your dependency packages been poisoned? This is where the SLSA framework and SBOM come in. Under an AI architecture, the system not only auto-generates SBOMs, but when a log4j-level vulnerability breaks out, AI agents can iterate through all your microservices and automatically generate PRs to upgrade the dependencies. All you have to do is review and merge. On the stability front, modern SRE philosophy argues that 100% availability is neither possible nor economical. We use SLOs and error budgets to balance release speed with stability. A step further is chaos engineering, where we proactively wreak havoc in production to test system resilience. When AI is involved, the system can instantly assess the blast radius the moment a fault occurs and complete a rollback in seconds. This microsecond-level self-healing is something humans simply cannot achieve. When your microservices scale into the hundreds and span across multiple clouds, how do you manage costs? How do you keep hundreds of developers aligned with consistent standards? That brings us to operations and platform governance. We've all seen test environment machines left running for months without anyone using them. FinOps exists to solve spiraling cloud costs. AI plays a massive role here. It can analyze your historical load levels and tell you that a particular pod actually only needs 0.5 CPUs, not the 4 you requested. This AI-driven dynamic right-sizing usually slashes 30% to 50% right off your bloated bills. How do we lower cognitive load? Through platform engineering. The platform team builds an internal developer portal, IDP. Business developers don't need to know how to write underlying K8s, YAMLs. They just click, create a new Node.js microservice on the portal, and the system automatically initializes the codebase, CI/CD pipelines, monitoring alerts, and security policies following what we call the golden path template. In other words, the platform encapsulates the complexity. Next, let's look at something a bit more hardcore. When building complex, long-running pipelines, how do you elegantly handle multidimensional concurrent tasks? Let's take the looping strategies found in modern platforms like Harness as an example. In pipeline orchestration, there are 3 advanced strategies you must master. First is parallelism, used to shard large tasks and speed things up. Second is the matrix strategy, which is perfect for cross-environment testing, like front-end compatibility or cross-platform builds. Third is repeat, used to iterate through simple lists. Proper use of these 3 strategies can reduce your pipeline configuration code by over 80%. Let's look at the code implementation for parallelism. This YAML shows how to evenly distribute testing tasks across 4 runners. Notice the system variables here. They dynamically inject the current node index and the total number of nodes at runtime. Your test script uses these 2 variables to automatically fetch its own subset of test cases. This is vastly more elegant and scalable than manually writing 4 different execution steps. Now look at the matrix strategy. Let's say you want to test your code on different operating systems and node versions. If written by hand, you'd need 6 steps. But with the matrix strategy, you just define the dimension arrays. The system automatically calculates the Cartesian product and spins up the corresponding instances. You can even use the exclude syntax to filter out invalid combinations. This is the beauty of declarative orchestration. This is an age-old pain point. It works fine in QA, but it crashes in production. Relying on detailed deployment documents doesn't work. Humans make mistakes. The fundamental solution is B, infrastructure as code, or EAC. You write all your server configs and network topologies as code and put them into Git. Your dev, test, and production environments are all spun up using the exact same code, completely eliminating environmental drift. When we hand over life and death power to an AI agent, the biggest question arises: how do you prove it's reliable? What if it hallucinates and deletes the production database? This brings us to agent reliability engineering. The first step to making an agent reliable is context engineering. LLMs are smart, but if you don't feed them the latest business data, they hallucinate. So before an agent executes anything, it must pull real-time states via MCP, and we enforce a strict rule: if it doesn't know, it fails. No guessing allowed. Secondly, we need to monitor the agent's thought process. If its confidence for the next step drops below a certain threshold, the system must intercept it. Absolute autonomy equals absolute disaster. We must establish safe autonomous constraints. First, scripts written by an agent must be dry run in a sandbox. Second, strict permission controls mean an agent cannot overstep its bounds. Third, and most importantly, human in the loop. For high-risk operations like modifying database schemas or changing production networks, the agent acts as a senior advisor. It drafts the plan and the risk assessment, but the person who finally hits enters must be you. Tying everything we've talked about today together, this is a complete AI-native software delivery closed loop, from AI-assisted coding on the left, to intelligent test pruning, to progressive delivery. Post-launch, FinOps and chaos engineering provide continuous monitoring. The moment an anomaly occurs, self-healing. Agents intervene, feeding root cause analysis and remediation suggestions directly back into the developer's IDE. It is a constantly self-evolving living organism. As we near the end, let's quickly recap the most critical hardcore terms from today. GitOps solves environment drift. MCP solves AI context retrieval. Test intelligence solves pipeline congestion. IDP solves cognitive load. And every architectural design we make is aimed at controlling the blast radius. These terms will be the cornerstones for how you design modern delivery architectures in the future. If you only remember one thing today, I hope it's this quote: stop obsessing over writing incredibly complex Bash or Groovy scripts. True architectural evolution is moving from static automation to a dynamic, context-aware autonomous network. That is the only way out of system complexity. So, what should you do when you get to work tomorrow? Please, don't try to tear everything down and start over. First, assess your cognitive load. Then find your slowest pipeline and introduce test intelligence to secure a quick win. Next, consolidate your most tedious configuration work into an IDP. An AI-native architecture isn't something you achieve just by buying a tool. It's a comprehensive evolution from mindset to architecture. Thank you all for listening.